Okay, so I'm gonna use the slides just for a moment, and then I'll get to the board, which is probably a little bit like a slower. Okay, so let me recap some of the things that I introduced yesterday. So remember that I'm gonna be working with one-sided choral domains. So I'm using Ahlfors David regular, but Hervé told me yesterday I should say Ahlfors regular. But Keith David is not in the audience, so maybe that's all right. Kind of, you see, with Steve Hofmann, we always say Ahlfors David regular, but with Tatiana, we are not allowed to put David on the name. So I kind of my brain is kind of half divided between one or the other. Anyway, Ahlfors David regular or Ahlfors regularity, which means that any surface ball, which is this thick area that is the intersection of a ball sitting with the center of the boundary, is comparable to R to the n. This is for all locations and for all radius up to the diameter. Okay, and then remember we have the corkscrew condition. The corkscrew condition is a quantitative openness, meaning that for any ball of radius r, I can always insert a ball inside of radius comparable, and this constant is uniform. Okay, and this point that I will use typically notation x delta or x cubed, depending if I'm working a cube, is called the corkscrew point. And then we also have a similar condition when we talk about connectivity. So the connectivity, remember, is this Harnack chain condition, which says that given 2 points, I can find a sequence of balls so that the diameter of the ball is comparable to the distance to the boundary. And also I have the number of balls, which is at the end the length of the chain, depends on the ratio between the distance between the 2 points and the minimum of the distances to the boundary. Okay? So the two examples that I'd like to keep you in mind is these two examples on which maybe each of the conditions can be violated. So no corkscrew means that it's so narrow that you cannot insert a ball of comparable radius. So it's something like a cusp. And no Harnack chains is the situation on which you are kind of getting the ratio between the distance and the relative distance to the boundaries is like 1. But then since you have to start with balls whose radius is comparable to the distance to the boundary, then the number of balls is increasing if I approach to the boundary. So this will violate the Harnack chain condition. Okay, so remember, just to finalize with it, is that one-sided choral domain satisfies the interior corkscrew, the Harnack chain, and Ahlfors David regular. And I'm going to introduce this character, which is going to be a constant, the constant that is involved in this condition. So for instance, we have interior corkscrew and Harnack chain with constant m, so which means that this small c is going to be m to the negative 1. So m is supposed to be like a large constant. And I haven't introduced the constant of the Harnack chain. It's better not to put them because it's kind of like a technical condition. But anyway, there is a constant that measures how good, for instance, how long or how many balls do I need in order to get this Harnack chain condition. And also the Ahlfors David regularity is constant m. Here you have two inequalities, so let's put m on the right hand side and then m to the negative 1 on the left hand side. Okay, so this is the setting. All right, so remember also that I am working with divergence form elliptic operators of this fashion, and I'm gonna call lambda, this capital lambda, the ellipticity constant. And then remember that I'm working with symmetric just for convenience, but there is no problem with that. And this is, you see, this constant capital lambda measures the L infinity of the L infinity condition of the coefficients, and also this accretivity on the matrix, right? So that I can quantify. And then yesterday I mentioned A infinity, and I put A infinity in terms of a reversal inequality. This is an equivalent formulation, and also it's convenient to have just one constant. So I say that this is an A infinity with constant n, and we have the following thing. For every surface ball and for every Borel set inside delta, I have this thing. The omega of f over omega of delta is smaller than m, which is a large constant, and then sigma f, sigma delta to 1 over m. Okay? So this is, again, a way to quantify because it's going to be important. All right. So the result that I introduced yesterday that can be, you see, either combining the work with Steve Hofmann and Ignacio Uriarte, or the work with Jonathan Sam, Steve Hofmann, myself, Kay Nystrom, and Tatiana Toro, or the work with Hofmann and Toro, this is what we proved yesterday. So if we have a choral domain with character M1, this is the constant that measures all the interior and exterior corkscrew and the Ahlfors regularity. And then I have an elliptic operator with constant, which is constant coefficient. So now this is a constant matrix with ellipticity lambda. and this is in an infinity with another constant m2, then omega satisfies the exterior corkscrew with constant n naught, which is a function of m1 lambda m naught. So this means that all domains with this constant, all elliptic metric with this constant, satisfying the A infinity with this constant, are going to have this with the same constant. And it's important because I need to quantify this, because in the following result I'm gonna make like I'm gonna proceed by contradiction, so I need to be slightly careful about the constant. Okay, so this is what we did yesterday. So remember, in order to show this, we remember the exterior corkscrew is something about geometry. I was able to tackle this by writing this exterior corkscrew as a Carleson, as a packing condition, which is an analytical condition, and then I use harmonic analysis. I use also PDEs and integration by parts argument in order to show this result. So now our next step, remember yesterday I sketched the proof. I say the first step is constant coefficient, the second step is with this metric satisfies this Kenig-Pipher condition with a small constant, and then today during the afternoon, I'll consider the general case when we have this Kenig-Pipher condition with arbitrary large constant. Okay, so today I'm going to be focused with the case with a small constant. So this is the result. So this is a joint work with Steve Hofmann, myself, Svetlana Mayboroda, Tatiana Toro, and Zhao 2 years ago. So this is the way. So I have to be careful. I know that this is kind of cumbersome, all these things about the constant, but I have to be careful with the constant, because this is what we teach our students. We are going to need to consider the negation of the statement, so we have to be careful in which order the quantifiers are set. Okay, so give me m1, lambda, and m2, which are constant greater than 1. And remember, n naught is this constant that I put there, right? So which is precisely given by the previous result. So I'm going to take 4 times n naught applied to this. This is just thing that I have a large constant and I make even the constants huge. But just forget about this number. It's just it depends on the same constant, but probably because I'm gonna be losing constants in my process, I will need to take like very huge multiplication of this constant. Okay, so I consider these things. So given this is a set. I set this number. N is a set number given with these parameters. So then I claim that there exists some epsilon depending on these quantifiers, so that if the following happens, then I have a exterior corkscrew. Okay, if omega is a bounded Corner domain with character m1, I have an elliptic operator with ellipticity lambda. I have an A infinity condition with constant m2. And then I have this Carleson condition, this Kenig-Pipher condition with constant smaller than epsilon. Oh, the epsilon should be the same. This is the same kind of epsilon here. Okay, so these are the quantifiers. This is my choice on n. So given the quantifiers, I choose n, and then I have this condition, and I'm going to be working only with bounded Corner domains. It's not that probably we know how to do it with unbounded, but it was more convenient to do it bounded. For today, in the afternoon, I will show that I only need it for bounded domains in order to get the full result. Okay, so then I can show that the exterior corkscrew holds with constant n. Okay, so this is my goal. So my goal is to show this result. Okay, and I'm gonna maybe it's better if I look at what is on the board. So let's consider so I'm going to proceed by contradiction. So one has to be careful because there are so many things. Okay, so what is the contradiction? This is given is like for all. So the negation is that we have some set of parameters, and then n is given by this set of parameters, so that for every epsilon j, we can find a bounded Corner domain with constant m1, an elliptic operator with ellipticity lambda. I have this condition with this epsilon j that is going to be a sequence going to 0, and then I know that I have an A infinity condition with constant m2, and I know the exterior corkscrew fails with constant 1 over n. Okay, so this is what is contained in here. So this is the negation of the statement. So I would like to get into a contradiction, assuming this. Okay, so epsilon j is a sequence that goes to 0. I have all these domains. I have this smallness here, which is gonna give me something later. And this is the contradictory conclusion. The corkscrew condition fails with constant n. Okay, which is prescribed, given the set of parameters, right? So this means the following. This means that for every j, I have a point sitting on the boundary. I have a radius, which is smaller than the diameter, such that the exterior corkscrew means that I cannot insert a ball of radius rj over n inside this thing. Okay, so this is exactly the meaning of not having the exterior corkscrew. Okay, so this is my setting. So I put this here because this is what I'm gonna do. And so the first thing I would like to do is because I can always move things and take dilation, so I can rescale. I can assume that the point qj is equal to 0 and the radius rj is equal to 1. Right, because I can take my domain omega j, so I move it so that the qj is now 0, and I rescale by 1 over rj. And remember, all my conditions are scale invariant, so moving doesn't change any of the conditions, and rescaling doesn't change because they're scale invariant. So then I can assume that this is a point which is in all the boundaries, which is going to be good because in terms of compactness, and the corkscrew fails with radius 1. And this is convenient. This is a convenient thing. So I know that there is no ball inside. There is no ball inside B01 minus omega j, because this is the exterior with radius 1 over n. Okay. So I'm done with the slides. I'm gonna move this up. Okay, so it's convenient now to introduce some notation. So now I have a sequence of domains. So I'm going to be working in this setting. I'm going to use sigma j to denote the Hausdorff dimensional measure and dimensional measure restricted to the boundary, and it also delta j is going to be the distance to the boundary, which I'm going to need in a moment. And also I'm going to use this notation. CJQR is going to be the interior corkscrew relative to this ball. Okay, so right, so this is the ball of QR, and I'm gonna denote CJQR, the corkscrew associated. Remember, this is 1 over M1 with these my parameters multiplied by RJ. Okay, so this is the condition that I'm gonna use. Okay, so this is going to be the interior. This is a point that is going to be fixed from now on. It's an interior corkscrew. Remember that 0 is on the boundary of every domain. And by the way, I think I forgot something, is that the RJs have to be, remember that the diameter, because my corkscrew is always up to the diameter of the domain, the diameter is always greater than 1. Right, because the corkscrew condition is only occur in radius up to the diameter. So if I'm thinking that this is, at least there is this ball, it means that the diameter has to be greater than 1. What I don't know is, you see, I have a collection of omega j's. I know that all omega j's, they sit on the boundary, right? So they sit on 0. So maybe this is 1, maybe this is another one, maybe this is another one. I don't know if they are bounded, but I don't know, for instance, if they converge to something which is bounded or unbounded. And actually, one has to consider two cases. Okay, so in order to do this, it's convenient to fix some point which is going to be a corkscrew up for the diameter. It is like the center of the domain, in a sense. Okay, so this is going to be a corkscrew for the ball centered at 0, which is on the boundary, in omega j. This is effectively like a course. This is like a, if this is your domain and this is 0, this is like a center, because it's going to have a ball which is of radius of the order of the diameter. So this means that these are the distance of the diameter. If you were thinking that you are probably in the disk or something like that, you could pick maybe the center of something, like you move from the center. Okay? All right. So this is xj here. So the size of xj, because this is the 0, is comparable to the distance to the boundary, and this is comparable to the diameter of omega j, which, because it's bounded, this is the same as the diameter of omega j. Right? If my domain is bounded, the diameter of the domain agrees with the diameter of the boundary.
So xj is not the center, it's the whole.
It's like a, it's the center of this ball, which is this corkscrew, but it's effectively like a center of the domain. So the domain doesn't have a center, but somehow it's a point whose distance to the boundary is like the half of the diameter, which is like saying that this is like a center of mass or something like that. Okay? So this is what I'm assuming. All right. Okay? So I'm probably going to put here that Gj is going to be the Green's function, right? I'm put some condition on the Green function later, and I'm going to also use the notation omega j for this thing, right? So this is all the notation that I'm going to use. Okay. And this is this point, which is going to be fixed from now on. As I said there, this is greater than 1. So I'm going to be passing to subsequences all the time, and I'm going to use the same notation all the time. So I'm going to use omega j, and then you see at every step I will pass to a subsequent, and then a subsequent, so forth, so on. Okay, so I have two cases. Either passing to a subsequence, and without changing the notation, I have the case on which this converges to infinity, or I have the case where this converges to some R0 which are 1. Okay? I have this is a sequence of numbers which are greater than 1, so I have infinity numbers. Either I have that there is a subsequent that converges to infinity, or there is a subsequent that converges to a number. So, and one has to, the argument is not that different, but I'm going to be focused on this case. So, in a sense, this is saying that my domain is, the domains are kind of blowing to something which is unbounded. And then I'm gonna forget about this case. Right? So the argument is not that different, but somehow this is a little simpler to be presented. Okay. All right. So in particular, in this case, because of this condition, I know that my point xj goes to infinity, right? Because xj is comparable to the diameter of this, which goes to infinity. Again, passing to a subsequent. All the time I'm passing to a subsequent without mentioning. All right. So at the end, what this thing is going to do, what is going to happen is that you are having these domains, and in the limit, you're going to see a constant coefficient operator associated to a delimiting domain. But I need to show that the limiting domain has all the properties. But the idea is the following. I have this sequence of omega j. These omega j's are going to be something unbounded. The limit is going to be a domain with the same, maybe it's going to be a domain with maybe constant 100 times n1. I'm going to have a limit on the elliptic matrix with maybe 100, then and so forth, so on. And the point is, like, because of this smallness here, this is going to tell me that in the limit, the gradient is going to be 0. So that means that there is going to be constant. And now I can use the constant coefficient. So that's somehow the outline of the proof. OK. Okay, so I'm going to pick this solution for seed in omega j. Okay. This is the green function. I'm dividing by, this is the harmonic measure of this. Of course, the harmonic measure is supported on the boundary. So even if I say the full ball, I'm meaning that this is the harmonic measure of the surface ball. And maybe I need to remove the xj because the green function has a singularity at the point. Okay. That's the difference between case 1 and case 2. In case 1, because you are going to infinity, you need to normalize so that this function doesn't vanish. If you are doing in this case, the only thing that you are going to have a singularity, and then you don't have to divide by this, and somehow the limit of the uj's is going to convert to the green function in the limiting domain. Here, this is going to converge to the green function with pole at infinity because my xj goes to infinity. So that's not the idea. Okay, but we will see this in a moment. Okay, it's also convenient. So this is my omega j. So my uj is defined here. This is the xj, which is kind of the center, so which is where the singularity is. I may assume also that uj is equal to 0 outside. So the green function is the fundamental solution, but with 0 boundary terms. Right? So the green function is a function which is like the fundamental solution, which is 1 over and minus 1, but with values 0 at the boundary. So if and it's continuous all the way to the boundary. So if I extend the function by 0, it's going to be still a continuous function. It's going to be a solution inside, but not at this point. Okay.
Shouldn't we put delta of 0, 1 in the omega j?
No, it's 0, 1. It's 0, 1 because it's somehow.
It should be on the boundary. It should act on the boundary.
And this is what I said before. The harmonic measure is supported. So when I say this, the harmonic measure is supported on the boundary. So I really, but then I need to put delta j. So I want to kind of, right? But it's the same thing because the harmonic measure is supported on the boundary. So even if I put a solid ball, it only sees the boundary. Okay. So let's prove the following proposition. So what we are going to see is that these uj's passing to a subsequent, we have the following properties. So first of all, there exists a function u infinity which is going to be continuous in the whole space. Okay, so that uj converges to u infinity uniformly and compacta. And then I have a convergence on the gradient. Actually, it's not only that, the u infinity is also in w1 to log of Rn plus 1. And this converges weakly in L2 log. Okay? So I have a limiting function which is going to be continuous everywhere, and it's going to be w1 to log, and the gradient converges in L2 log. Okay? Second, suppose that I take this set. So one has to think what is u infinity. U infinity is the green function for this domain with pole at infinity, right? So you think what is the green function? The green function, you think that you are thinking that the green function is 0 outside. The green function is actually attached to the domain so that the domain coincides with the point for where the green function is greater than 0. So this is what I'm saying. So suppose I define this domain. So then I have this convergence. I'll tell you in a moment what I mean by convergence of sets. Okay, so this is going to be unbounded, right? And I have this thing. The convergence is only for closed sets. I know that the boundaries of omega j are going to converge to the boundary of omega infinity, and the closure of omega j is going to converge to the closure of omega infinity. Okay, give me for the moment. This is just some convergence. I'll put it in a moment, and then third. Okay. So I can show that this satisfies the interior corkscrew and Harnack condition with maybe 10 to the 10 m, whatever, some constant multiplied by the m1 that I have originally. So this means that the domain, the limiting domain, is a domain with the same properties as before, by maybe losing some constant. And then this is only about the interior, and I need something about the if the boundary is Ahlfors regular or not. And now the thing is a little bit different, because the omega j's do not converge to the Hausdorff measure on the boundary, but converge to something which is comparable to the Hausdorff measure of the boundary. So there exists u mu infinity, which is Ahlfors regular with constant 10 to the 110 m1. So meaning that this is satisfied, it has the is Ahlfors regularity. So with this constant, which is a very bad constant, so that omega j conversely weakly to mu infinity, the support of mu infinity is, so it's a measure which is supported on the boundary, and these two measures are comparable. In particular, is Ahlfors regular or Ahlfors regular? Okay, so it's not. I'm not saying that I know that the sigma j's converge to the surface measure, but what this is saying is that this converges to something which is eventually comparable to the Hausdorff measure, and here again the constants are of this order. Okay, and these are comparable, meaning that the set of every set here is comparable to the set of every set here. Okay, all right. So let me maybe put here what I mean by the convergence of sets. So convergence is a local convergence in the Hausdorff distance. So I said that Ej converges to E, which are closed sets, if the following happens. So for every R, Ej, I don't know if I put the pole or not, is Ej goes to 0. Okay, so it's a local convergence in the Hausdorff sense. So what this is saying is that in every ball, I can make sure that E is close to Ej and Ej is close to E. And these are not the same things, because, for instance, you can have things like this with a big hole, and then one is close to the other, but the one is not close to the other, right? Because there is, for instance, suppose that I have something like that. There is no point that is close to the set here. So it's saying that they are not only close, but also if there is a hole. You see, there is a hole in the other thing. So this is a pretty strong. This is a pretty strong convergence. So the convergence in the Hausdorff distance, but in a local sense. Okay. All right. So I'm gonna try to prove some of these things so that you can see what are the tools that I'm using, and then eventually I will get to to the end of the proof. So I think I'm not going to have time to finish in this lecture, but then I will make the next lecture a little bit shorter, and that's all right. Okay, so let's do the following. So let me start with the proof of 1. So let me fix some fix R, and remember I know that my xj converges to infinity, so I'm going to assume that xj is not in this domain, and this is true for every j large enough. Okay, so that the idea is that I'm going to be working okay, so my xj is away from this ball, and then eventually we'll let r goes to infinity. So what are the properties that I have? So look at my function uj. So remember that uj is a green function divided by some normalizing factor, right? So the green function, as I said, first of all, I'm assuming that it's 0 here. I'm looking just at this ball, so uj is identically 0 here, is identically 0 on the boundary, and then I'm away from the singularity. So uj is well defined here. In particular, I know that Lj of uj is equal to 0 in B0 for R intersection omega j. Okay, so I have a solution because the only place where the uj is not a solution is at the singularity, but I am making sure that my singularity is not in this ball. So this is a solution in here. Okay, so what I need to know, I want to use like a compactness argument to say that uj converges to something, so I need to use Ascoli-Arcellar theorem. So this is what I'm after. Okay, so let me remember this is R. I have the ball of radius 1, and this is going to be this pole Cj of 0, 1. Remember my notation, this is the corkscrew relative to this pole, so it's a point here. And I want to show that this is comparable to 1. Okay, so what is this? So this is by definition, I have Cj okay, so then there is this estimate called Caffarelli-Fels Mortalla Salsa, which compare harmonic measure with green function, which says the following: if I have G, let's put it this way. Okay, so this is the following. It says that the average of the harmonic measure for some ball delta is the green function. This is in general for any elliptic operator, is comparable to the green function of this over the radius of the ball for every x which is away from B, and delta is B intersection partial. Okay, so this is the connection between harmonic measure and green function. So that is why it's convenient to have the green function there. So now suppose that I'm using this, right? So this is the corkscrew. This is the corkscrew with respect to delta. So I'm using this with the ball of center 0 and 1. Right? So what is this green function? This green function is going to be the pole, and I know that my xj is away from the ball. So I'm going to have this at the point xj of delta j 0, 1, or let's put it B0, 1, multiplied by, remember that this is like R delta to the n. But R delta here is 1, so this is like 1, right? So I will have, if you want, 1 to the 1 minus n. Right, because this is the radio. And then I'm having here the same thing below. So this is like 1.
Delta in your estimate in the CFMS,
Yeah.
delta is not centered at the boundary.
No, it's centered at the boundary. It's always centered at the boundary. So
But then x delta
it's the corkscrew. So x delta is the notation that I use for the corkscrew.
is not the center.
No, it's the notation. So x, the ball is centered here, and x delta is the corkscrew point. Okay, if I take the center, the green function is 0 at the boundary, so it makes no sense. Okay, so this is what this is saying. So what this is saying is that my uj in this point is of the order of 1. So it's non-degenerate. And this is for all j's. Okay. And as I said before, one have to be very careful with the constant, because I will send j to infinity. So what are all these constants depend? All these constants depend on the character of the domain and on the ellipticity. But all of them are uniform. So this is, and this is very important, this is uniform on j. Okay? So I have that at this point that depends on the domain, but at this point, this is uniform on j. So with this estimate, I'm going to look at my uj, by the way, is the green function. My green function is positive, so I'm going to look at the supremum on this, now on this set. Okay? So there is this property of, which is called a Carleson estimate, for harmonic functions, or for solutions of the elliptic operator, which are 0 on the boundary, the supremum agrees or is comparable to what happened at the corkscrew point. And this is because of the following thing. So I'm going to write it. This is controlled by u at the corkscrew associated to 0r. And I don't know if I need to put like, I think I'm going to put 2r to be safe. Okay, so this is saying the following, that the sup of the, because u is identically 0 here, my uj is 0, in this elliptic theory business, solutions that vanish on the boundary are actually they are Helder continuous at the boundary. So if they are Helder continuous at the boundary, this means that they are going to be very tiny here with some quantitative control. But once you know that they are very tiny here, the supremum has to be attained here. But by Harnack's inequality, all these points are the same. So I can just pick the corkscrew point. So this is what I'm saying there. I'm not writing the proof, but this is actually the proof. So I repeat this. So functions that are solutions that vanish continuous on the boundary are C alpha near the boundary. So this means that if this is 0 and this is C alpha near the boundary, I can make this smaller. I can put here maybe an epsilon r j, which is my epsilon r, and this is going to be pretty small. So we mean that the supremum has to be taken here, right? Because this is positive. But in all these points, I can use Harnack's inequality because I'm away from the boundary. So by Harnack's inequality, and I'm using Harnack chain, so this depends on Harnack chain constant, I know that this is comparable to this point. Okay? And now, I'm at this point, right? So I'm at this point. This is, remember, this is 2r, and this is 0, 1. So I can move from this point to this corkscrew point. Of course, this is going to depend on r, but my r is fixed, and I have to do it for every r. So this is, again, another use of Harnack. With constant depending on r, I can write this. This is uj. Okay, I can move from a point. Remember what was the Harnack what is the Harnack chain condition tell me? It tells me that I have a chain from this point to this point. Maybe I have to be a little bit more exaggerated. So maybe this is my point here, Cj, 0r, and this is my point, Cj, 0, 1. But I have a Harnack chain joining this point with this point, and then how many balls do I have? Because in every of these balls, I'm going to use Harnack's inequality. So what is the length of the chain? Remember, the length of the chain depends on the ratio between this distance, which is of the order of r, And what is the distance of this to the boundary? Is of the order of r, and this is of the order of 1, which is the minimum is this. So the length of the chain is going to depend only on r. So I have all these balls here. In each of them, I use Harnack's inequality because it's a positive solution. I need to have a positive solution, so I need to make sure that my pole, the Cj is away, Xj is away from this. So I have something depending on r. And this is like 1. Okay? And of course, this is greater than 0. Okay? All right. So my uj is uniformly bounded in B0R. Because remember that it is 0 outside of the ball. So I have that this is bounded here, and here is, this is 0. Right? So this is a uniformly bounded sequence. As I said before, because this vanishes on the boundary, this is also of C alpha. And I can use interior estimate. So actually, one can show that this is even equicontinuous. Indeed is indeed Helder alpha for some exponent alpha. This combines the estimates near the boundary because the solution vanishes on the boundary with the interior estimates, the Georginas-Moser. Okay, so then I have a sequence of uniformly bounded functions in 0R which are equicontinuous as Collier-Sella says that passing to a subsequence, and I will relabel the subsequence, there exists which is going to be also, if you want, equicontinuous in 0R, so that uj converges to U infinity. So I'm cheating a little bit because I'm working in 0R, so I know that there exists a sequence that converges in this ball, and I have to do it for every r, but now I do one of these diagonal ways on which you send r to infinity, you put r the integers, and then you send it to infinity, and this is the point. So at the end of the day, this kind of argument, together with Collier-Sella, together with one of these diagonal arguments to take this limit, says that I have this limiting function, which is the first part of this thing. The only thing that I need to know now is the W1 to log condition. But this comes from Cacciopoli's inequality, because if I do okay, so remember that my uj is just a solution here which vanishes on the boundary, but if you have a solution that vanishes on the boundary and then you extend the solution by 0, is a sub-solution, and Cacciopoli works for sub-solutions. So I'm using here Cacciopoli for sub-solutions. So this is Cacciopoli for sub-solutions. uj squared. But again, you see it. Remember that I saw that this is bounded. So this is with constant and depending on r. So now I have, this means that uj so I have the supremum of the W1 two norms of the gradient of the uj in W12 is bounded, and then using Banach-Alaoglu, I know that there is a weak limit, but I know already that my uj converges to U infinity. So the weak limit has to agree with U infinity. So this says that U infinity is indeed in W1 to log, and I have convergence weakly of this thing. Okay. All right. So this takes care of the first part. Let me. I think, how much time do I have? 5 minutes or 3-4 minutes?
10 or 15.
10, 15, okay.
15.
Okay, we'll start later. Okay, that's good. Okay, so let's move to the proof of 2. I'm not going to prove 2 in. I'm not going to prove the whole thing, but at least I would like to give some of the ideas. Okay. So first of all, this is an open set because u infinity is a continuous function. I just saw this in the first step, and it's not empty. And what is not empty? Because, so remember that the corkscrew is always in the ball. So all the CJs are in the ball of 0, 1. So again, I have a sequence of points which is in the, which are maybe in particular they're in here. They're in a compact set. I can pass to a subsequence, so I know that CJ 0, 1 converges to C infinity, some point at some limiting point. And remember that I know that uj is like 1, right? And I know that uj converges to u infinity in compact sets. So in particular, it's easy to see that u infinity of C infinity has to be greater than 1. This is a combination of these limits and the key continuity. Okay, so the CJ is very close to C infinity, and I know that uj of C infinity is like is going to be like 1. Okay, so this is not empty. Okay, so now let me observe the following. So as I said before, 0 is in the boundary of every omega j. So in particular, this is not empty. Okay, and then for all j. So if I have a sequence of sets which intersect a ball, then I can, there is like a compactness argument for this convergence. I know that there is a limit in that sense. So I know that there exists, passing to a subsequent, this convergent to some closed set. So again, this is a compactness argument. This is the same, the same order of this kind of thing, right? So I have a sequence of points which are in a compact set, so I can always pass a subsequence. The same thing is here. If I have a sequence of closed subsets which all meet a closed set, the same closed set, then I can pass to some subsequent which satisfies this convergence. Okay, and then the same, of course, can be done for the, because in particular also this is not empty. Okay, so this is not empty because the 0 is always in this point. So again, because I have a closed set that intersects a fixed closed set, I know that there is a subsequence. Again, it's a subsequence that converges to this. The goal is to see whether this is equal to this and whether this is equal to that, right? So this is what I don't know. Okay. So let me show, or let me at least give some idea to see, for instance, why this has to agree with this. Okay, so for instance, let's start with this. Okay, so let's take P in this. Because I know that this converges to this, in that sense, I know that the P has to come from a collection of points here. So I know that I have a Pj converges to P, and this is in the boundary of Fourier omega j. This comes from the convergence. But in particular, Upj is 0, because remember, Uj of Pj is 0 because Uj vanishes on the boundary because it's the green function. So this is 0. Okay, and then notice that one can see that because P is a compact set, the point is a compact set, I know that U infinity is the limit on compact set of the Uj, so P is a compact set itself. And then I know that this is 0 because P is very close to Pj, and Uj at Pj is 0. This is an equicontinuity argument. Okay? So this means that U infinity of P is equal to 0. But then what is the definition of omega infinity? The point for U infinity is greater than 0. So this means that P is not in omega infinity. Okay? So this means that it's either on the boundary or on the exterior. So suppose suppose that P naught is not in there. Okay? And let's get a contradiction. All right. So let me put it this way. This is an open set, so there is a ball which is contained in there because this is an open set. And remember that outside of this, my Uj is identically 0. So Uj, even is Uj, yeah. No, U infinity is going to be identically 0 because omega infinity is by definition the set where U infinity is greater than 0. So in the closure, it has to be identically 0. U infinity is always at least greater than, right? So U infinity is greater than 0, and omega infinity is the point where U infinity is greater than 0. Right? So this means that U infinity has to be 0. In this ball in particular, in the closure by continuity. Okay? All right, so let's look at let me evaluate Uj and the corkscrew for the relative to the point Pj and eta over 2. Again, because the Pj, depending on P, I can use Harnack, and this is going to depend on P and eta, but I can move to this point. Right, because you see, this is again the same thing. I have to look at the distance between 2 points, and of course this is going to depend on P, and this is the distance of this point is like eta, the distance to the boundary of the point is like 1. So again, I can do this for a fixed P and a fixed eta, I can do this, and this is always true. Right, these points are eta over 2 away from the boundary and 1 away from the boundary. Okay, and remember that this was like 1. Okay. But now, Uj of z, I can put it as Uj of z minus U infinity right? Because I remember u infinity is identically 0 on this ball, right? And this goes to 0, right? Because I know that uj converges to infinity in compacta, uniform compacta, so this goes to 0. So this says that uj of z goes to 0 in this ball. But this point probably make this is sorry, this is in P. There was a P. But this point by construction is in this thing. So then I get a contradiction because I know that uj goes to 0, but I know that uj is like 1. So this is a contradiction. So this means that this is a contradiction. So this means that P has to be in omega infinity closure, but it's not in omega infinity. So P has to be in omega t. Okay, so you see, this uj function is what can allow me to prove all the estimate, because it's, in a sense, the uj is the green function which kind of represents the domains, and the u infinity is the same as the domain. Okay. Okay, so we have to look at the converse, but this is even like easier because I now have to look at what happens if I have to show this. But suppose that I'm going to show actually the converse. I'm going to show that this is not in omega infinity. But this is kind of, I can actually, omega infinity is a closed set. So if P is not in here, it means that there is a ball. Suppose that P is in here. There is a ball that is away from omega infinity. But remember that I know that my omega j is in, there is convergence in here. So it means that my omega j is going to be around here. So this means that either P sits inside the domain omega j or outside the domain omega j, but in particular is not in the boundary, because the omega j is very close. So P cannot be in the omega j, the boundary of omega j is so close to omega infinity that P cannot be in this thing, right? Because you are kind of far away. So that's the proof. So this is as easy as it is. Okay, so this takes care of the second thing, at least the boundaries. And the argument for the closure of the domain is similar. It's always this kind of tricks. And it's always using the U to know that something, right? Because at the end, we know that omega infinity is the set where U infinity is greater than 0. So we must use the U infinity in order to show our result. OK, let me, just to finish, let me show 3. I'll skip 4, but let me show 3. So why the limiting domain satisfies the same conditions. And again, it's almost like a picture. So let's look at the proof of 3, and let's start with the interior corkscrew. Okay, so I need to take P on the boundary and 0 smaller than the diameter, but remember the diameter is infinity. Okay, so first of all, because P is in the boundary and I already know that the omega j converges to the omega infinity, it means that P comes from a sequence of pj's in the boundary of omega j's. Right? And remember that I know that the boundary of omega j converges to infinity, so I may assume that R is smaller than diameter. Okay, just to make sure. So for j large enough. Okay, so this is what I'm doing, and then so how do I prove the interior corkscrew? By using the interior corkscrew for the omega j, which are uniform. So I'm gonna take the Cj with half because I need to adjust the constants. So I'm gonna take this. Okay. All right. This is the interior corkscrew, so I'm using here interior corkscrew for omega j. Okay? So because the pj is very close to p, and this is of the order of r over 2, this is contained, saying, in the ball of center p 3/4 of r. Right? So, or even in the closure if you want, right? So I have a sequence of points which are all in a compact set, so passing to a subsequent, I know that Cj converges to some point C infinity, which is in this ball. Okay? This is going to be my candidate. So how do I know that this is the corkscrew? So let's just draw this thing, right? So this is my omega j, and this is my omega infinity, because they converge, so they are very close. So how is the Cj? The Cj is a point, and now the Pj, so the P is going to be here, and the Pj is going to be very close, right? And this is a corkscrew, which means that I have a full ball. So this is where the Cj is. But the C infinity is very close to Cj, so it's going to be that close, right? So now you look at the picture and remember that I took here r over 2. So this C infinity is actually corkscrew for omega infinity, maybe with constant 4 times m1. Remember that I have m1 for this. So this is just this thing. So what is a corkscrew? A corkscrew is a point which is contained in the ball, and what is the distance of the boundary here? It's r over 2 to pj. But pj is so close to p that it's going to be also, so the C infinity is going to be of the order of r, or maybe 3/4 of r, and that's it, period. Okay? So this is the proof of the interior corkscrew. This is just proof by drawing, but this is what's going on. So how is the proof of the Harnack chain condition? It's the same. It's the same. You can just draw it, because, so let's look at the Harnack chain. So now I have x and y, which are in omega infinity. But because I have that this converges to this converges to this, again my omega, this is omega infinity. This is going to be my omega j. Right? The distance for j large enough, this is comparable to this distance. So the x and the y are going to be contained in omega j, in omega j for j large enough. This distance is comparable to this. This is just this picture. And the same occurs with y. So now I have 2 points which are in omega j, and in this distance, so I can use the Harnack chain condition for omega j. This is the Harnack chain within omega j. And I know that the distance of the chain depends on the distance between the 2 points and these distances, but the distances are of this order. So the same Harnack chain that I have for omega j is valid for omega infinity. So this is this thing about this convergence, that this convergence says that things has to be very close. And that's the proof. And that's the proof. The only thing that, and I'm going to finish now, so the only thing that is left is this, which is a little bit more delicate, but again, it's a compactness argument, because you have to do it, this is omega j, sigma j, if you restrict it to a ball, it's a finite measure, and then it always is the 0, and then it's a doubling measure, so you can actually show that you have something, a sequence of radon measures, which they always see the same ball and they are doubling, so you know that this converges to this weakly. If you converge to this weakly and this is Ahlfors a bit regular, this has to be Ahlfors a bit regular, and the only thing is to show the, but this is the only thing is to show the support thing, but the support thing has to be with the thing that we show, that I know that omega j already, the boundary converges to the boundary, and that's it. It's a little bit technical, but not a big deal. Okay, so I think I'm going to stop here. So for the moment, and continue this afternoon. So for the moment, what I have is like a limiting domain, and I have a very nice u infinity, which is going to be a green function. And now from this point, the only thing, so notice that I haven't used neither this nor this, right? So these are the things, and this is the key. So what I need to know now is what happens with these matrices as z goes to infinity, and then what happens with the infinity condition as z goes to infinity. And that's the end of the story. So it will take me 10 minutes this afternoon, or maybe 15 minutes, and then I'll use the rest of the time to prove the large constant case, so to give a sketch of the proof. Okay, so thank you.